okay, part 2 of the exercise that we had from before. So what I did here, like I said, was rewrite and rearrange the last expression that we had. I just separated it into two parts. I broke it into two parts, okay? The first part is this, which contains the notable trigonometric limit which we obtained. Okay, so I'm separating this part right here. As you can see, here's our notable limit. Okay, and the second part is this one. Okay, the part which, you know, still has to be worked because it still has an indetermination. Okay, sine of a minus sine of a is going to be 0, and at the bottom I'm still going to have ax minus a, which is 0. So the second part is this one. Okay, they share the denominator because it's just addition of fractions. Okay, you should be aware of this by now. So first part and second part. Okay, first part and second part, here they are. First part and second part. Now, on the first part, okay, we're pretty much done with the indetermination. So like I said, this is 1 because of this property, okay? And cos of A is a constant, okay? A is a real number. It's stated at the beginning of the problem. So if I do, let's say, limit of k, and let's do it in another color, limit of k, and k is a constant, sin of x over x, or sin of whatever over whatever, this is going to be equal to k. Okay, because 1 times k is k. And in this case, k is cos of A, it's a constant, okay? So we know that this equals 1. But we'll simplify this in a bit, okay, when we evaluate. Now, this is where we have to work on, okay? Let me erase the bottom part. And the same reasoning that we had before, we're going to apply to solve this, okay? We have somehow do something to that expression so that we can obtain a notable trigonometric limit, okay? So the first thing that we're going to do is do a common factor, because I see that we have sine of A on both members of this abstraction. So let's do a common factor, sine of A, and let's rewrite it, okay? I guess we can do it right here, okay? It's going to look like this. Sine of A, common factor of cos of x minus A minus 1, okay? Now, this looks a little bit familiar, and we can even do a little bit better with a common factor, okay? Let's get the minus sign out of the expression so that we can make it look a little bit nicer, okay? So this minus goes out, and minus times plus is minus. So this we're going to reverse the order of it, okay? And it's going to look like this, 1 minus cos of x minus A with sine of A as a common factor, okay? And now, this looks a little bit more familiar. Why? Because, well, do you remember the identity property? 1 equals sin square of x plus cos square of x. Well, this looks a little bit like this, okay? But we can even rearrange it to say something like 1 minus cos square of x equals sin square of x. Okay? And this looks a little bit like this. The only thing missing is the square. So how do we get the square to appear here? Well, that's pretty simple, okay? All we have to do is keep in mind that we have notable products. And that is x minus A times x plus A equals x squared minus A squared. Okay? So in this case, he is going to act as the x, and he is going to act as the A. Okay? This is the same example. It's like basically doing a conjugate on this expression so that I can get this. So what I'm going to do is multiply by the conjugate times 1 plus cos x minus A over 1 plus cos x minus A. Okay? This is again following the property of notable products, and this is so I can get this to look like this, okay? This to look like this, because then I'll have the sin square of the argument. So let's erase this. And I'm going to end up with limit, again, the first part of the expression is taken care of, x tends to a, and we're going to have sin of x minus a cos of a over x minus a. Like I said, this is already taken care of, minus, because we did the common factor minus, this times this times this, because the property that we had is going to equal 1 minus cos square of x minus a, right? Multiplying sin of a. And at the bottom, I'm going to have x minus a multiplying 1 plus cos of x minus a. Okay? So, what do we do now? Well, this right here, because of the property that I had before, is the same thing as saying sin square of x minus a. Okay? This is equivalent to saying sin square of x minus a. Okay? That's it. So we do this here. Erase. And rewrite. Sin square of x minus a times sin a. Okay? I just rewrote it. Here, we use, again, the notable limit. Just like here. Because as you can see, we have been able to find the same argument for top and bottom. Of course, there's one little detail. There's two sins, okay? There's sin of x minus a times sin of x minus a, hence the square. So we only get rid of one sin, okay? Okay? It's like having sin of x minus a times sin of x minus a. This is exactly what I have right here, over x minus a. The notable limit is going to allow me to get rid of only one of them, which is this one. Okay? But the denominator will be gone, because I got rid of it with the notable limit. This stays, but this is gone. Okay? So, let me erase this. I get rid of one, and I get rid of this. And now, I can even rewrite the whole expression. And here, I can get rid of this too, because I've been saying it for quite some time. I'm going to have cos of a. Now, I got rid of the indetermination on every single element of the function. So let's evaluate. When x tends to a, cos of a stays the same as a constant. When x tends to a, what happens here? Well, a minus a is 0. So sin of 0 is 0. Okay? This is 0. Again, when x tends to a minus a is 0. And sin of 0 is 0. Times sin of a. 0 times anything is 0. So right here on top, I'm going to have 0. Let's do it right here at the bottom. Cos of a minus 0 over, and at the bottom, when x tends to a minus a is 0. Cos of 0 is 1, and 1 plus 1 is 2. So, cos of a, 0 over 2, 0. So, this is the answer to the exercise. Cos of A. Pretty long, but still very worth it. So what happened here? Let's rephrase real quick, okay? What we wanted to do was always somehow obtain the notable limit, okay? Somehow make it appear in both elements of the equation. We got it here, okay? And we also got it here doing certain arrangements, okay? We got rid of the square and the x minus a, so this is why we had 1 sine of x minus a left. But still, we got rid of the lower part of the equation, okay? Then we just evaluate. When x tends to a, cos of a stays the same because there's no x right here. And then, in this case, we have a minus a, 0, sin of 0 is 0, times sin of a is 0 on the top. And then at the bottom, a minus a is 0. Cos of 0 is 1. 1 plus 1 is 2. And 0 over 2 is 0, which means we are just left with this as the answer for the exercise, okay? Pretty long, pretty hard, difficult, but it's a beautiful accomplishment once you're able to solve it, okay? Like I said, trigonometric limits, they're not easy. They involve a lot of practice and a lot of knowledge regarding properties. And we're going to keep doing more exercises, okay? See you in the next video.